So in this video, we're going to talk about potential energy diagrams, which are these kind of hill-shaped graphs that you see on page 8. Page 8 is all that we're doing as a homework podcast. We will go on to page 9 stuff later in class, but we only need to do page 8 to get our stamp and answer the embedded questions at the end. So these potential energy diagrams show the amount of stored energy and how that changes throughout the reaction. And that's important to remember because this stored energy isn't necessarily going to be able to be felt as heat. This is how much energy is stored in the chemical bonds of our chemicals. And we're going to talk about two different kind of perspectives on these reactions. Earlier in this year, we've seen some reversible reactions that had those arrows pointing both ways before. And so we do have a forward reaction moving from left to right and a reverse reaction where we're moving from right to left. So just to kind of put that together, the forward reaction begins with what we normally call the reactants, the stuff at the very far left before the arrow. And it's producing what we normally call the products, the stuff after the arrow. And the reverse reaction is the opposite. It begins with what we normally call the products, but these are the reactants of the reverse reaction. And it ends with what we normally call the reactants, which are the products, the things being produced in the reverse reaction. And what we need to keep in mind, especially since we're in this energy unit, we've been using these words endothermic and exothermic. If the forward reaction is exothermic, then the reverse reaction is going to be endothermic. This is kind of like in Hess's law, when we had to flip a reaction's direction to get it to match what we were looking for. We flipped the direction, we flipped the sign on the delta H. So that turned endo to exo or exo to endo. And if the forward reaction is endothermic, the reverse reaction will be exothermic. And you can see that using this chemical reaction example that is written down below. We have our energy term here on the reactant side. So it's going into this reaction with that water to produce the H2 and O2, which means that forward reaction is endothermic. That energy that was separate from the water molecules is now getting tied up in the bonds of these H2 and O2 molecules. The energy is part of those molecules. But if we reverse that reaction, if we're turning our H2 and O2 into water and energy, then they were producing energy. It's exothermic. The energy is being released, coming out of those bonds, and it isn't needed for the H2O bonds. So that extra energy that isn't being used to make the H2O bonds is released as heat. So the next thing to fill out here is a little quick blurb before we start actually looking at and analyzing those potential energy diagrams. There's another type of energy that we need to know about, and it's called the activation energy. And you can see that here in these graphs. My graphs have a little bit of color in them. It's these red areas, which I've marked as EA on the graphs, and here EA by the word activation energy. I know it seems backward for it to be EA instead of AE, but that's the energy of activation. So E with a little A on it. And this is the word that we use to describe the minimum amount of energy required to get the reaction started. It's kind of the extra energy we need to get it rolling. The reactants, the starting point of our reaction, already have some energy. So we're not measuring the total amount of energy that they have. We're asking how much more energy do they need to get going. I kind of think of this like when I roll out of bed, I've got a little bit of energy. I know that because I'm awake. My eyes are open. I can walk around. But I don't get actually rolling. I can't get on the road, come to school, do my work until I have at least 1 cup of coffee. So my 1 cup of coffee is my activation energy. It's the energy I need to get to my peak energy. And on these graphs, and I'll talk more about the calculations and kind of some other work that we can do and calculate, but I wouldn't think that it's a bad idea to write this here again, even though we'll have some better words for some of these points later on. But we calculate the activation energy by subtracting the top of the peak energy number. If I had a number for how much energy that I have at this point, and I have a number for the energy that I have for my reactants, the starting point of my reaction, then subtracting those two numbers will find me that difference between my starting point and my peak energy. And that number is our activation energy. And even here without numbers, we can see that these two different reactions with these two different graphs have different activation energies. And the bigger that activation energy is, the more energy you need to get active, get going. That's generally a slower reaction. Like someone that needs 2 or 3 cups of coffee before work, before they can get going with their day, is going to take longer to get going than I do with just 1 cup of coffee as my activation energy. So that does affect the rate of the reaction, but that's not really our focus here. But we can see those differences in our activation energy a little bit better with these graphs. So let's get more into these graphs, especially comparing these exothermic graphs to the endothermic graphs. So the first thing that we should kind of notice and point out here is that the reactant energy there at the very far left is greater than, it's higher than the product energy for exothermic reactions. And that shouldn't be too surprising because, as we know, in exothermic reactions, energy is being released. It's exiting from our system. So whatever energy level we're starting at here with our reactants, if that energy is being released, then the product energy is going to be lower. We're going to have less energy in our products. And keep in mind, if this is exothermic, if energy is being released from our system, from our chemicals, that means it's going from the system to the surroundings. And that means that our delta H, our enthalpy value, is going to be negative. We're losing energy. And these graphs do also have that enthalpy labeled on them. Notice how it's the difference between my reactants and my products that shows us how low we drop, how much down we went when our reactants turned into the products of this exothermic reaction. And because it is down in energy, that delta H value is always going to be negative. And just as a quick little reinforcement of that idea we've been talking about, because the surroundings is where we are and where we're observing and feeling this energy change, then these reactions, these exothermic reactions, will feel hot or warm because we're getting energy moving out of the chemicals into the surroundings where we can feel it. So we're going to feel that energy increase in the surroundings as heat. So please make sure you got all of these things down. I know we've talked about a lot of these ideas already once, but seeing them and kind of visually on these graphs is going to be important. All of these ideas are reinforced in this visual way using this graph. And we're going to talk about all of these same things with our endothermic graphs, starting with, well, which one has more energy, and the energy of our reactants or our products. Here in our endothermic reactions, the products have more energy because that system is absorbing energy, which means energy is moving from the surroundings to the system. And that means the system's gaining energy, getting more energy, and it will have a positive delta H number. Notice how here our delta H is still the difference between the reactant and product energy, but here, because we're going up in energy from the starting point, from those reactants to the products, this is going to be a positive value. We're gaining energy there. But keep in mind that energy that the system is gaining isn't necessarily going to be felt as heat by us. That might get tied up in the potential energy, the stored energy in our chemicals. So just like a battery can store energy without feeling hot, we're storing that energy in our chemicals, which means that it's going away from the surroundings where we can feel it, which means that this reaction would feel cold. Now, there's one last little thing at the bottom of the page that we're going to fill in. But before we kind of finish up thinking about these graphs, I do want you to sketch a little hill diagram. Just keep it simple with the 2 axes and the hill between our starting and ending point. And you might have space for this kind of back up top where we were writing some of those first stuff about energy being absorbed or released, endothermic and exothermic there. It doesn't have to be big, but I do want you to be able to label some key points here. And so I want to talk about what each of these points are and how it relates to the things that we might ask you for. So Keep in mind, all of the stuff we're about to talk about is for the forward reaction. In class, when we move on to the next page, I am going to ask you to do some stuff with the reverse reaction, but I kind of want to be there to help you with that. So, like we saw in those diagrams up above, the beginning point of our reaction, the beginning point of our graph over there, not near where it touches the y-axis at kind of level A, is always going to be the energy of the reactants. And at the very far end of the graph, we have the energy of the products. That's always going to be where our reaction starts and ends, and where our graph starts and ends. And then the other important point that we need to be aware of and be able to kind of find is point C. C is what we call the activated complex. Now, don't get that confused with the activation energy. The activation energy is how much energy we need to get up to this point. Notice how this arrow C goes all the way from the top of that hill all the way down to the bottom axis, just like our reactant and product energy. This is a different set of chemicals that we call the activated complex. It's always going to be the tippy top of that hill where we have the most energy happening in our reaction. And this is kind of just a big squishy mess where all the reactants are all trying to become products, but they're kind of halfway there. And it's this big kind of mess of bonds and kind of partial bonds being formed and broken here. And we call that the activated complex. That's where we are activated. It's always going to be the highest point on the entire graph. And then the activation energy is B. Like we talked about before, this is the difference between that tippy top of our hill and where we started with the reactant energy. So even though I said top of the hill minus reactants, here I would start to use and kind of reinforce the fact that that tippy top of the hill is what we call the activated complex. So we're going to do the activated complex minus the reactant energy if we're trying to find that activation energy. It's the energy we need to get activated. It's not the total energy we have at that point. It's just the partial energy, the energy we needed to get there from our starting point. And then, of course, we have enthalpy is D. That's always the difference between where we start and where we end, the reactant and product energy. And just like every other time we've calculated this from numbers, we're going to do products minus reactants, always. So products minus reactants calculates enthalpy, even when we get a graph to help us find those numbers. So one last little comment, a couple last little blanks to fill in at the bottom of the page. And this is the word catalyst. Catalysts are a special chemical or enzyme, if you're in a biological system, that lowers the activation energy, which increases the rate of the reaction. And so if I use a biology example with enzymes, this is lowering the hill that we have to pass over. If this is my original reaction here with this red line, adding a catalyst to that reaction doesn't change where my reactants or my products energy are. It just lowers the hill in between. But if you think of that like a little person maybe trying to walk to school, it will be quicker if I have to walk or kind of go over a smaller hill as compared to a bigger hill. Even though the same distance between 2 points is the same, climbing a bigger hill will take longer. So that's all that a catalyst does. Notice that it does not change our enthalpy because our reactants and products are the same. The difference between them, that enthalpy number, is still the same. It just lowers our activated complex, which lowers the activation energy itself. So at this point, we're done filling out information on this page. But the rest of your questions to earn the grade for this podcast is about answering some embedded questions here. And so I want you to look at each of these graphs. I'm going to show you these potential energy graphs and answer the question in red at the top of the page. And I'm going to show you that question now, but at some point in the next 10 seconds that I leave this on the screen, the question will pop up embedded in the video for you to answer. So this graph that I want you to look at, and I know I have some extra information here. I'm going to kind of clean it up for the rest, but I wanted to get you some other information about these. But just focus on the actual line, the curve here on the graph, just based off of that shape, and maybe a little bit involving the information I've given you here. Try and tell me, is this endothermic or exothermic? For this next graph, same question. I've taken out a whole lot of the extra information that I have there, so you're going to have to base it off of the position of these reactants and products, or about the general shape of this graph. But is this reaction endothermic or exothermic? I know I did specify the forward reaction in both of these, but that just means normal, left to right. In this reaction, I want you to think of the reverse reaction, going from the products to the reactants. Would going from products to reactants be endothermic or exothermic? Here, I want you to tell me and try and find the energy of the activated complex. Keep in mind, this is not the activation energy, this is the activated complex. If you don't know what this is, then you didn't pay attention to those little bit of notes where we labeled points A, B, C, D, E. So go back, rewatch that part of the video, take those notes someplace on that page, and that will help you find your activated complex number here. And then finally, you are going to need to calculate this, do some math to calculate the enthalpy of this reaction, the delta H value for this reaction. If you're having any trouble finding any of these answers in this video, in these embedded questions here at the end, then please come to class with questions. Be ready to ask those. Let's go over those, and then we will be moving forward in our packet on the next couple of pages.